very important parameter here, and we usually do not cover in our curriculum, UG curriculum or even otherwise. But what we realize that this transmission ratio has a lot of impact on the overall stiffness, and we try to understand with a very simple example. So, what do you mean by transmission? And usually the question we may have, and usually when we are designing or putting the components and trying to assemble, we do not know like where to put the spring. So, we know that some compliance is required, some stiffness is required, but what is the location, where we should put it, and what is the like point of application of force F. So, with respect to that, where this K is placed, and that placement will have a big bearing on the overall stiffness at this point F. So, call it K 1. So, in this case, what is there? So, you have a simple plank here, and suppose you attach a spring at the tip and where you are interested, and you are applying force F and having a stiffness K. So, what will happen? Yes, K is defined. So, of course, K is F over X, that deflection. So, this is the deflection we get, right, and that is the stiffness we experience here as well. So, it will be, so K 1, that is what we are saying, K 1. What happens if we have this thing? So, suppose this is the point of application F. Now, we move to some other locations. What happens if I put this spring here? What will happen? So, whether F, whatever F I am choosing here, and the stiffness here. So, there will be some associated deflection here. What is that deflection? And what we realize that, right, if we want to make the free body diagram, it is like a lever now, because if you take the bar and there will be a spring will try to pull it, right. So, it is F. So, there will be some force F here, which is function of this leverage. So, take balancing, if we just try to balance the moment at this point O, what we realize, this is the length L, and suppose this is length, or this call it A and this is B. So, what will be this F now? F prime, call it. So, if we just try to balance, what we realize, F into L is equal to F prime into B, and then F prime is simply F into L by B. So, L by B, that ratio is there, and here since it's like inside, so this L by B will be definitely more than 1. So, this force will be higher, it is going to be higher than F. So, but the spring here, now F prime is acting on this. So, the deflection here will also increase by the same amount, del prime. And what happens when it comes to this point, again there will be leverage, and what happens, the deflection will again getting multiplied. So, what we realize that there is a multiplication, multiplying effect, it is not just linear. And we have one case here. So, suppose we just shift it from here to here. So, in the middle, midsection, at the middle, what happens? So, I think very, very easy to work out, but we realize that the force, the F prime here, is to F, because it's A is basically L and B was L by 2. So, n times F. So, this gives you 2F. So, L cancel and 2 will go up and we get 2F. But if we apply 2F here to the same spring K, now 2F is applied. But we realize that the deflection here is 2x 2 times. It's already increased. Earlier it was only x. So, you apply x is how defined f by k. Now, same k, now 2f is applied. So, this will be 2x. Now, again go back and because of the leverage, the deflection will be 4x. This is the delta. So, now if we talk about the equivalent stiffness K, which is F over delta. So, F is same, but now delta is 4x and so K equivalent F by x is K it's a K, that is how we defined K here. And 4, if here we know that the point of application, the output and in is a L divided by L by 2. So, that ratio is 2 and if we try to write in terms of 2 that ratio, what we find that there is a square term and that is why we have written here that the equivalent stiffness is K over 2 square. So, you move to the midsection inside, but you lose stiffness and how? It's square times. So, placing any member or any stiff or compliant member having value k, it will have a lot of effect on the equivalent stiffness and this is the one example to just to illustrate that. And so, we can write in terms of the transmission ratio also. So, as I said, so if we write transmission ratio as I, which is V out by V in. So, V in is with respect to where we are placing the component and V out is the point of interest where we are applying the force or where we are like getting the output. So, here and here or you can. So, here the ratio will be definitely now 2 in this case and if we try to just generalize and later we will try to also look at it and what we see that we can always write that if I is the transmission ratio, the equivalent stiffness will be K over I square. So, huge impact on the stiffness and this if we know, then we will also try to see like in the design, check in the design what. So, just moving the spring can affect the overall performance. So, if that K equivalent is different, all the vibration requirements, your omega 0 values all will get affected because of that. And if we know this, I think by now we should be able to also appreciate why certain phenomena or certain things happening not expected earlier.